In Pakistan, 144 million people do not have access to reliable electricity, with frequent rolling blackouts. There is an abundance of irrigation canals in the Peshawar region, with most having between 0.5 and 2.5 metre head range. We believe that by designing an ultra-low head hydropower converter, we can harness this clean resource to provide reliable electricity. There are no commercial products available that can be used, so the aim of this project is to design a solution to this problem. We will be basing our design on an undershot wheel because it maximises the height difference of the water, whilst also directing all the flow into the blades of the wheel. A ski jump will be used to aim the jet into the blades, which can be positioned at an ideal angle of inclination and can be lowered completely to allow debris to pass. The power takeoff was developed by the previous GDP project, using 2 sets of friction rollers to replace a traditional gearing system. Our design innovation for this project comes in 4 parts. Firstly, we have created a scaled model of the design of the ski jump and hydro wheel to test our design. Secondly, we have analysed the geometry and the number of blades to have an optimal energy capture from the water jet. We've improved the power takeoff system by utilising railway theory to redesign the wheel and roller contact to increase friction and stability of the wheel. Lastly, the wheel structure uses a more rigid metal frame to withstand the loading better, taking away pressure from the perspex discs that now just hold the blades. To test the wheel, we needed to design and create a hydraulics rig, a scaled version of the site in Peshawar. This had to be a cost-effective design to just support the channel and water loads, whilst minimising material used. For the design of the wheel, the main improvements needed from the previous project were to improve the friction, stability and the strength. Therefore, we utilised railway theory to tackle these problems. The old perspex and nylon rollers were changed to be metal on metal. This would reduce wear and increase friction. The rollers in the outer rim were altered to mimic a train wheel and track to increase stability. The load was now taken by the wheel's metal frame, with the perspex size just holding the blades, increasing strength. With the wheel and roller design sent off to be manufactured, we started building the hydraulics rig and blades of the wheel. When the hydraulics rig was fully assembled with the pump system, the ski jump was then added. The support structure was also erected at the same time, supporting all elements of the wheel and power takeoff system. The position of the centre of the wheel and the rollers to the ski jump was established using theory and graphical software. We could then begin to test the wheel. Here are the results for our experiments.